Swayam Prabha. Digital India. Educated India.
Good morning. In the previous lecture on optimization, we studied the conceptual framework, conceptual background of multivariate optimization. In this lecture, we will be studying some of the methods to solve optimization problems. Now, some of the methods are called direct methods, that is because they use only the function values and not derivatives. And one direct method we will study first, and then we will continue into the study of methods based on gradients also, that is steepest descent, Newton's method and hybrid method. So, first the direct methods. These are some of the direct methods, and some of the methods are very simple in operation, and one of these methods I will use here for elaboration, that is Nelder and Mead's simplex search method, and all these methods utilize only function values and do not use the gradients or derivatives, and therefore they are of great value for those functions which are not differentiable, that is which are not differentiable at several points in the domain. For such functions these are quite important, because derivative based methods will not be appropriate for such functions. Even when derivatives exist, derivatives are defined, there also quite often we find that using this kind of a method which does not use a derivative is helpful if the derivative evaluation is computationally quite costly. However, whenever derivatives exist, we use a method which uses derivative, because using derivatives every step of the algorithm can make longer sweeps. So, first we study a derivative free method or direct method, that is Nelder and Mead's simplex search method. Now, those of you who have a background of linear programming, they know that there is a simplex method in the linear programming methods also. Now, this simplex method is different from that, and this is for nonlinear problems, and that is why to differentiate it from the simplex method for LP problems, we call it as Nelder and Mead's simplex search method. Now, first thing, what is a simplex? In two-dimensional space, a triangle is the simplex, that is a polygon composed of 3 vertices. In three-dimensional space, a tetrahedron is a simplex. Now, in two-dimensional space, among triangle, quadrilateral, pentagon, hexagon and so on, what is so special for a triangle? The special property of a triangle which is not shared by any other polygons is that triangle by nature is convex. For example, if I give you 4 points in sequence A, B, C, D, A, B, C, D, the quadrilateral that you form out of it in that sequence does not have to be convex. See, this is not convex. On the other hand, if I give you only 3 points and ask you to frame a triangle, you cannot frame a triangle without the triangle being convex. So, by nature, by definition itself, a triangle is a convex region. That is an advantage. Similarly, in three-dimensional space, tetrahedron, as long as it is non-degenerate, that is all the 4 points are not in the single plane, in that case the tetrahedron cannot be formed. So, a tetrahedron is by nature convex to begin with. Similarly, in an n-dimensional space, a similar geometric entity, a similar geometric figure, a polytope composed of n plus 1 vertices is a simplex. So, a triangle is a simplex in two-dimensional space, that is a plane. A tetrahedron is a simplex in the 3-dimensional space, and in n-dimensional space a polytope formed with n plus 1 vertices is a simplex. Now, Nelder and Mead's method iterates over simplices that are non-degenerate. To begin with, we must give it a simplex which is non-degenerate, that is, all the n plus 1 vertices do not fall in a single hyperplane. That kind of a simplex we have to give in the beginning, and then the method's step, the typical iterative step of the simplex method will ensure that at one step one vertex of the simplex method will be replaced by a new vertex, and like that the simplex will keep on changing iteration by iteration, traveling towards a minimum point of the function. Now, framing initial n plus 1 vertices which form a non-degenerate simplex is actually not very difficult. For example, if you take one point in n-dimensional space, then finding additional n points in order to form a non-degenerate simplex is easy, because from this point if you move towards x1 direction by a little amount, then x2 direction by a little amount, and so on. So, like that n directions among the coordinate directions itself you will get, which will give you additional n points, and this original point n plus 1 points. So, that will be a simplex which will be non-degenerate. So, in 2D plane the corresponding thing is that corresponding situation is that whatever point you take, from that move in the x direction a little and y direction a little, and then you get 2 further points, and this is a valid triangle. No chance of all the 3 points falling on the same line. So, like that developing n plus 1 points which form a non-degenerate simplex is actually easy. You develop such a simplex and start the iteration. Now, in the typical iteration, beforehand we evaluate the function at these n plus 1 points, and after developing the function values, after evaluating the function at these points, we identify 3 of the n plus 1 vertices. The point xw, the vertex xw, which is the worst point, where the function value is the worst, that is highest for a minimization problem. The best point xb, where among these n plus 1 vertices the function value is lowest, and the second worst point xs. Now, in one iteration of the simplex method, this worst point xw will be replaced with a good point. How to do that? So, we try to find out the center of gravity of the face not containing xw. So, in this simplex of n plus 1 vertices, every collection of n vertices define a face. Now, that face which contains all the vertices except the worst point, the center of gravity of that face is found by simply adding the position vectors of their vertices, its vertices, and dividing by n. Out of the n plus 1 vertices, n vertices are included here, that is excepting the worst point. So, therefore, divide by n. So, this xc is the center of gravity of that face which does not contain the worst point. Now, for example, suppose this tetrahedron is the simplex and this is the worst point. Now, the center of gravity of the face not containing the worst point will be the center of gravity of this triangle. So, suppose this is here. Now, from xw to xc, if we draw a line and extend it further behind, then this is a point which is the reflected point. Reflection not by this plane, but against this point. Okay. Why we do this? Because among the vertices of the simplex, if this is the worst point, then from this plane, from this hyperplane, this side is a bad side. So, we try to go on the other side. So, we come from xw to xc and further go behind by equal amount, and that is the reflected point xr. So, that is this xr. Now, this xr is the default replacement for xw. Now, other than this default replacement, we can consider several other options. See, default option is here, where this reflected point, this is xw, this is reflected point xr, and this line segment, this line shows the face not containing the worst point xw. So, this is xr, which is the default new point to be used for replacing xw in the simplex. There can be some other possibilities. For example, if it happens that we find that the function value at xr, f of xr, f at xr turns out to be better compared to even the best point that we have right now. Among the current vertices of the simplex, whatever is the best point, compared to that also, if the reflected point is better, that will mean that this is a very good direction to go forward. So, in that case, we may decide not to stop at this point itself, but to go further. So, that means we will expand the simplex, not keeping it of the same size, but we will expand the simplex and go here. This is x new. So, if the function value at xr turns out to be lower than function value at x best, then we consider an expansion of the simplex. On the other extreme, if the function value at xr turns out to be worse than the current worst point, that means that staying on this side of the plane itself is better, because on that side it is even worse. So, then we consider a negative contraction on the old side itself, not on the new side at all. On the other hand, if we find that the function value is between xs and xw, that is, it is better than the worst point, but worse than the current second worst point, even that means that it is not a great idea to go all the way to xr, because the moment we accept this and frame the new simplex, this newcomer will be ready for expulsion, because after the xw point is replaced with this, then this will become the worst point, because it is worse than the second worst point. So, that is why going to xr may not be a good idea, though this direction is good. So, in that case, we consider a positive contraction, that is here. So, all these special measures, expansion, contraction of either kind, can be effected through this kind of measures. That is, if the reflected point is better than the current best, then we expand, that is xc plus alpha into xc minus xw. Alpha equal to 1 would mean taking xr itself. So, alpha is greater than 1, that is, that will bring us here, the simplex will be expanded. If xr is worse than the current worst point, that is here, then negative contraction, that is xc minus beta into xc minus xw. So, beta is between 0 and 1. So, that will give us this kind of a point in between. Okay. That way the simplex will get reduced in size. In this case, where xr is better than the worst, but worse than the second worst, that is in between the two worst points currently, then we consider a positive contraction. This, in place of this minus sign, we have a plus sign, the rest of it is same. So, the simplex is nevertheless reduced in size, but it is brought to this side. And if the function value at xr, the reflected point, turns out to be worse than the current best point, but better than the two worst points at present, then we take the default value, default point, which is the reflected point itself. This is a typical iteration, and as this iteration goes on, then finding good directions, the simplex is expanded in order to explore the search space, and when good directions do not come forthcoming, then the simplex is reduced through such negative contractions and positive contractions, and slowly the size of the simplex goes down, and that way squeezing the minimum point. So, finally, the termination condition for the method is when the vertices of the simplex come extremely close to each other, approaching the tolerance or accuracy required by the problem. So, this is one very good method which uses only function values, and it operates remarkably well for most of the problems. However, if gradient is available, then that is, if the function is differentiable and the derivatives can be developed without too much of computational cost, then most of the time we use derivative based methods, because they are relatively faster, more efficient. So, the most straightforward method, conceptually simplest idea is that of steepest descent method or Cauchy's method. This is typically a line search based method, in which from a point xk, initially x0, the guess point given, and in intermediate steps the current point, the current iterate. So, from a current point xk, a move through alpha units in a direction dk results in this kind of a situation, f of xk plus alpha into dk, which will be up to first order approximation will be alpha into gradient transpose dk, right. Now, this is the first order, up to first order. So, if you omit the higher order terms, then you find that this is the change in the function value. Now, if along the direction dk, if the function value decreases at least in the local neighborhood, then you call that direction dk as a descent direction. That is, for positive alpha, if this is negative, then the direction is called a descent direction. That is, along that direction an infinitesimal step will tend to decrease the function. And since our problem is that of minimization, typically we would like to operate along a descent direction. Now, if we are going to operate on a descent direction, then why not pick up that direction along which the descent is fastest or steepest descent, and that will be in the direction of negative gradient, because gradient of a function gives you that direction along which the function increases fastest. So, its negative direction will give you a direction along which the function will decrease fastest. So, if you take that direction, which is the direction of steepest descent, that is fastest decrease, that is the negative gradient. You can take minus gk, negative of the gradient vector, or the unit vector along that direction, it does not matter. So, after selecting that, if you select that direction, then the corresponding method is called the method of steepest descent or Cauchy's method. Then you say that after deciding the direction, we try to pose the problem to minimize the function along that direction, that is how far to go in that direction. First, we have decided which way to go, and the choice of that direction like this has characterized the method of steepest descent, and then along that direction we want to now decide how far to go, that is the line search sub problem. So, if we want to conduct a line search along that direction, then we say that how far, what is alpha, how far to go, so that along that line the function is minimized. So, after decision of the direction dk has been made, this problem is a single variable problem, because we are trying to find out how far, what is the distance alpha that we have to move. So, f of xk plus alpha k we want to minimize with respect to alpha. So, this function phi of alpha is a single variable function. So, if we try to exactly minimize the function along this line, then the process is called exact line search. On the other hand, sometimes we conduct an inexact line search, that is decreased sufficiently, and then from there we try to work out a new direction, that is also in practice. In fact, more professional algorithms use inexact line search, but for the time being, to keep things simple, we talk of exact line search only. So, for exact line search, we will terminate at that point where along that line the function, while reducing stops reducing and then starts increasing again. That means, we are looking for that point where the function stops changing along this direction. Okay. That is phi prime is 0, at which value of alpha the phi prime, the derivative of phi with respect to alpha, becomes 0. If we differentiate this with the help of the chain rule, then we find gradient of this function at this point transpose derivative of this with respect to alpha, that is dk. So, this should be 0. So, we are looking for that point, that alpha k, where this will be 0. What happens is that if the function contours are like this, here is the minimum point, and if we have started somewhere, say at this point, then at this point the gradient is this way, orthogonal to the contour, and then negative gradient is this direction, and the steepest descent direction is this. So, in the steepest descent method, this is the direction along which a line search is conducted, and as we proceed along this direction, on the way contours are cut like this, and finally we approach a point where a contour is tangential to the direction. That is the point where the line search ends. That is the point where an exact line search would end. So, that is, as you cut the contours inward, the function value goes on decreasing, and at the tangential point it does not decrease anymore. Beyond that, you would end up cutting the same contours outward. So, you stop here at this point. Okay. So, this is the point where the gradient is in this direction and it is orthogonal to the current search direction. Initially, we started searching along a direction which was exact negative to the gradient, but finally we arrive at a point where the current direction is at right angle to the gradient direction. Okay. So, that is the end of one iteration. From there, the fresh gradient is evaluated, found this way, and the search in the negative gradient would go like this, which would be tangential to another contour here, and this is the way in which we will proceed. Okay. So, this is the method of steepest descent. Now, if you conduct exact line search in any method, then you will find that the direction along which the line search is made at the end of the exact line search, the gradient at the final point turns out to be orthogonal to this search direction. In the case of the steepest descent method, its negative will be the next search direction, orthogonal to decay. So, this is the way the steepest descent method works, and if you try to work out an algorithm out of it, then this is how it will look like. Selecting a starting point x0 and several termination parameters, tolerance values, etc., and maximum number of iterations. The termination condition for the steepest descent algorithm will be the vanishing of the gradient. If the gradient at a point is found to have very small magnitude, that is almost 0, then we stop, else we evaluate the direction, and then in that direction conduct a line search by minimizing this, and accordingly update the point x, that is xk plus alpha k dk, the result of line search, that gives the next point, and then we can check whether there has been significant change in the function value in terms of absolute tolerance and relative tolerance. If not much change has taken place, then we can stop. Otherwise, if the number of iteration exceeds, then also we can stop, which means that we are losing patience, we do not expect to have further improvement, and otherwise if the number of iterations is reasonable, not approaching the maximum allowed number, then we go to the step 2 again, evaluate check this gradient condition and continue into finding the next direction and so on. Okay. So, this is the typical loop. Now, one good quality, one great merit of this method is that it has excellent global convergence. That is, started anywhere, at every step it is assured that it will make a descent step and it will approach the minimum point. But why we put so many stops? Because in spite of having excellent global convergence, the method of steepest descent has a very poor local convergence. The reason for that can be analyzed if you consider the benchmark problem of minimizing a quadratic function like this. Now, minimizing this function and this error function is actually equivalent, because if x star is the minimum point of this function, then it is the minimum point of this function also, and the difference between these two functions is actually a constant. Now, therefore, while analyzing the steepest descent method on a quadratic function, we typically analyze it over this function, and through a long deduction you can prove that the ratio, the convergence ratio, first of all it has linear convergence rate, and then the convergence ratio of that linear convergence process, that is error at the next point divided by error at the previous point, is limited by this number, and this number is this number can be very large depending upon what is the condition number of A. For example, A is a matrix, the Hessian matrix A, and if you find that the largest eigenvalue by least eigenvalue of that Hessian matrix is something like 9, then you will find that this will be 8 and this will be 10, 8 by 10, and the square of that will be 64 by 100. That means 64%, which will mean that 64% of the error at the previous step is likely to remain in the next step. So, that shows that the convergence is quite slow, and this is why in badly scaled problems in which the Hessian is badly conditioned, condition number of Hessian is large, in such situations you will find that the convergence ratio is poor and the algorithm does not operate quite well. However, steepest descent method has its own advantages. One great advantage is that its conceptual understanding is direct. Conceptually, that is the simplest method that one could think of. Second is that in a completely new problem, it is advantageous to start the process with a steepest descent based method, because that has excellent global convergence, and this global convergence property also helps in the utility of steepest descent steps into other professional algorithms, which generate directions based on more sophisticated considerations. The more sophisticated considerations in more professionally sensible methods like conjugate direction method or Quasi-Newton methods may develop directions which most of the time operate better, but there are situations where even those directions turn out to be weak or poor. In such situations, typically one step of steepest descent method interspersed between steps of other method helps in regenerating the progress and the process of improvement of the function in a good manner. So, that is considered spacer steps. Spacer steps in other sophisticated methods are quite often used with the help of developed with the help of steepest descent method. Now, the concept of selecting direction and conducting a line search in that direction in this manner based on gradient is inherited also in the more sophisticated method of conjugate directions or conjugate gradient method. But what conjugate gradient method does over and above steepest descent method is at the first step it takes along the negative gradient, and then the subsequent steps it takes in such a well orchestrated manner, not necessarily in the negative gradient direction, that the work done in the previous steps are taken advantage of in the later steps. For example, this kind of in the narrow contour case, the steepest descent method quite often does a zigzag motion like this while approaching to a minimum point like this. That kind of demerit is remedied in conjugate gradient method, which is based on conjugate directions. So, that is a little more advanced method, which we will not be discussing in this course, though it is there in the book in chapter 23, but we will be omitting that chapter in our study here. Now, other than steepest descent or Cauchy's method, there is one more method which is called a basic method, and that is Newton's method. That relies on a second order approximation of the function based on a truncated Taylor series. So, for a function f x at x k in the immediate neighborhood of x k, the current iterate, the second order truncated Taylor series looks like this. This is the value of the function at the current point plus first order change plus second order change, with the higher order changes neglected. Now, for the minimum point in the neighborhood, if we try to consider the condition for vanishing gradient, that is the first order necessary condition, then differentiating this we will get this relationship, or the first order truncated Taylor series for the gradient itself which will be Gx roughly equal to Gxk plus Hessian into delta x. Now we say that in the neighborhood of xk, we try to look for that point where the gradient vanishes. That means this is 0. So if this is 0, then we can find out x minus xk, which will be negative of this pre multiplied with the Hessian inverse, that is this. So that is x minus xk. So for finding x, we have to add xk through that, and that is this. So this is a typical iteration, which is very much like the equation solving process, because this is also essentially equation solving process. The equation to be solved is gradient equal to 0, right. So this is the typical Newton's iteration formula for minimization. The great merit of this method is that it has got excellent local convergence. That is, local convergence is quadratic. See, the error in the next step divided by error in the previous step into error in the previous step squared, that is finite. That means at every step you will be expecting 2 orders of decrease in the error value. However, the point to caution is that this method does not have global convergence, something which is a bare minimum necessary for any optimization method, that it must have global convergence. The idea of global convergence is that at every step the function should decrease, or there should be an approach towards the minimum point. So Newton's method does not guarantee that. However, if started sufficiently close, it has excellent local convergence in the sense that it approaches the solution at a faster rate, if it does at all. On the other hand, if started far away from the optimal point, it may not approach the optimum point at all. It may go somewhere far away, because there is no guarantee as such that an xk plus 1 generated through this formula will be a point where the function value is lower than the function value at xk. That means that it does not have the property of global convergence. In the special case where the Hessian matrix is positive definite, in that kind of a situation also all that we can say is the direction suggested by Newton's method is a descent direction. Okay. That we can say, because if H xk, that is the Hessian matrix as the current point, is positive definite, then its inverse is also positive definite, and in that case dk with this formula will give you dk transpose gk as minus gk transpose hxk gk. See, minus this is the direction dk. With that you take the inner product of gk, that is gk transpose added here, put here, multiplied here. So you get this. So if the Hessian is positive definite, then this is positive for all gk, and that means with this negative sign this is negative, and that means the direction suggested by Newton's method, that is minus h into gk, is a descent direction. Even that does not mean that the entire complete step of Newton's method will be a descent step, because the direction may be a descent direction. Along that direction the function value might start decreasing, but in the entire complete step in between it might start increasing again. So it may be a descent direction only if the Hessian matrix, okay, this is inverse. So there are 2 points here. One is that if the Hessian is not positive definite, then it may be a, it may not be a descent step, the function value may increase, and it may not be even a descent direction. If the Hessian matrix is positive definite, then it is guaranteed that the direction will be a descent direction, though nothing can be said about the complete step. So based on this observation, we may think of the modification needed in the Newton's method for its developing into a worthwhile optimization method having global convergence property has then 2 aspects. One is the necessity of this Hessian matrix being positive definite, which as it is cannot be guaranteed at any point, because we cannot guarantee the positive definiteness of the Hessian